Okay, so my microphone's pretty sensitive, so you're going to occasionally hear my chair making squeaking noises and things like that. If pizza delivery or Taco Bell shows up, you might hear a doorbell ring. Um, if I get hungry, maybe you'll hear my stomach growl, and if I yawn, we'll all yawn together. Um, just wanted to sort of review a little bit about what happened on Monday at roughly, I don't know, probably 20 minutes till 6. The internet went out campus wide with no thought or reason as to how soon it could be resolved. It put me in a very difficult position, but one that we can deal with. Um, we had videos to watch, we had quizzes to take, and we had lectures to do that were all hosted on Canvas. And without access to Canvas, that really made that difficult. Now, I could have probably I know I could have transferred the lecture onto a thumb drive or something and brought it down to the lab and done it, but we wouldn't have been able to take our quiz, and we wouldn't have been able to watch the video, and it would have just put us behind by about a class, which means that there was really no good reason to have the meeting of the class given the situation. Now, it may well be that the internet was restored prior to our course starting time, but at roughly a few minutes after 6, I decided it was, in fact, time to notify everyone that we would not be having class. I had to go find some place where I could get good cell phone signal and then log into Canvas through my cell phone and send the email out to the students. So by the time I got done, it was probably closer to maybe 10 or 15 after 6, which is not a big lead. And for many of you who were already on the way, I apologize. But um, perhaps some of you it saved the drive in for what would have been no class. Others, I'm sure you didn't realize it till you got there and saw the sign hanging on the door. So if you made the trip in and didn't get to go to class, I apologize for that, but there wasn't really anything we could do. I was not willing to um, wait until everyone got there and to see whether or not we had internet and then make a decision at that time and send everyone home. So I hope you appreciate that effort on my part to not waste your time. And as such, in order to keep on track, I'm going to go through and narrate the slides for this week's lecture and post them on this week as well. I'll send out an email indicating to everyone that you need to go in and watch the slides, watch the video, and take the quiz. Now, on the upside, your quiz is now an open book, open note quiz, so that should make that a little easier. And in case some of you have a tendency not to check Canvas all week, I have set it so that the quiz, while due next week before class, the link will stay open an additional day. So if you arrive at class next week not knowing that the quiz is now open, note, and I remove the password protection element, that'll at least give you another day to work on it. So let's talk about some of the things here in this chapter. One of the big ones is data alignment problems, and what do we actually do? We go through a process called reproject, or basically what we do is we take data that is in one projection and we change it to a different projection. And when we do so, we make a new data set that is projected the way we want. And here we have two examples of the continental United States. Probably a more accurate term is the counterminous United States. It's not continental because Alaska's not there. It's just the contiguous lower 48. And in the center we see this black dot, so this says center of projection. And in both of these cases, that spot is the center of the US. It's the same spot for both. But as you can see, when we're looking at the green, Lambert conformal conic, or the blue, a Mercator, the configuration and shape of the continental US is pretty daggone different. And you can see how nothing really lines up. Well, if you're working in one and you need to be working in the other, the solution is to reproject, where you would literally go in and have the Mercator projection changed into the Lambert conformal conic. This would give you a new data set that would be projected the other way. So just to give you some more ideas of what we're talking about, here is I believe it's Australia, and we've got two different projections. The GDA 94 versus the GDA 2020. These are two different datums. If you remember, datum's just this way we fit some ellipsoid to a geoid. Apologize for the yawn. It happens every time I make a video. And so it's the fit of that, and then we use that to calculate our GCS, and then we use that to make a projected coordinate system, and so on and so forth. But in this example, you can see that when we have the two different projections of the exact same place and you try to line them up, they don't. Different datums require a mathematical transformation. And when that doesn't happen, you see things like this. This is an example of what can happen when you combine data sets. Now, this doesn't mean that these are in two different datums. This could just be the regular fit that happens between two different images. And so if you were to notice here, there's a line that goes up through the middle of this. You can't really make it out too much, and that line indicates the right image and the left image, and they should line up, but they do not. And the reason they do not is because when you make a transformation or a projection or change a projection, you're doing some sort of math element, and that element introduces error, and so not every point lines up perfectly with the other point. In this example, you see this because these two bridges, this one bridge doesn't line up and it looks like two bridges. So going back to what I had mentioned earlier a little bit, just to make sure we're kind of on the same page here, the brown is the topography and the surface. The dashed line is that spheroid, that ellipsoid that we're trying to fit to the gravitationally defined surface of the Earth, or the geoid, which is the green line. And you see that when we do this, there are some places where the green line is above and other places where the green line is below that spheroid. That's because we try to fit it as best we can for the area that we're interested in. In other places, it's not going to be as good, and even what we're interested in, there's going to be some variability. So let's take a minute and talk about this reproject idea. You take data from one projection and you change it to another. It's really not a big deal if the data is in the same datum. If you're in the same datum, you're working off of the same GCS, you're working off of the same ellipsoid that's been fit in the exact same way to the geoid, and so it's just a matter of reverting back to the GCS and then projecting it forward into the new projected coordinate system. It is a bigger deal if you're talking about different datums. When you talk about different datums, you're talking about going through this process of a transformation. And a transformation is basically a shift from one datum to another. A good example would be NAD 27 to NAD 83. They use different spheres, spheroids, ellipsoids, whatever you want to call it. As far as, there's some specificity. It's an ellipsoid, but to get it in your head, it doesn't matter whether you're visualizing it as a round ball or a round ball that's been flattened on the top and bottom, or whatever, however you can sort of visualize it. It's this shape, and then there's the real shape of the planet, and then there's this gravitationally defined sort of mean sea level kind of value that we have. Now, that is the geoid, and that is what we're going to call like zero elevation. And so we need to fit that ellipsoid, whether you're envisioning it as a sphere or a spheroid or however. We have to try to line it up. Now, they're two different shapes, and so they're not going to fit perfectly. But you can imagine that you could shift it around and make it fit as good as possible somewhere. And you do that by moving it around. And so that'll take care of it. Now, the other problem that comes into play that we have to deal with sometimes is when we have a missing spatial reference. And this is probably the bigger problem. When you're missing a spatial reference, it means your data cannot be displayed. Well, it can be displayed, but it can't be projected. In other words, you can show it in ArcMap, but you can't show it with other data. And that's a pretty significant problem. And the only thing you can really do is go through this process of being a little bit of a GIS investigator and looking at as much information as you can find about the data set to come up with your best guess of what it actually is in terms of its coordinate system. And then using a different set of tools, not the project tool, but the define projection tool, to go in and just set the projection to what you think it is. And then once you do that, you simply go and look and see if the data now displays properly. If it does, then you made the right choice. If it doesn't, well, then you got to pick another winner and make that change. So this might clear up a little bit of the talk about these ellipsoids and geoids. So here we've got the good old Earth, and we use gravitational measures to come up with this idea of what we think sort of the surface mean sea level kind of value is. And we're going to represent that with that darker, or that lighter blue line that circles around the sort of planet shape. Alright, now we have all these different ellipsoids, the GRS 80, the Clark 1866, the WGS 84, and the idea is that we've got to figure out how we can shift those around to line them up as best we can. And so in this example, this is sort of showing what that looks like. And you can see that the Clark 1866 sticks clear out past, and in the southern hemisphere it doesn't come near fitting, but it's designed to fit perhaps in a place like, say, North America, where it would probably be a pretty good fit. In other scenarios with some of these other ones, the shift from center is somewhat minor compared to the shift that you have with the Clark 1866, and it sort of shows that the approximate shift from center mass to the GRS 80 or to the WGS 84 looks to be in the neighborhood of about 2 meters, so it's a pretty decent approximation. The Clark 1866, to get it to fit to a place like North America, may have to be moved by as much as 236 meters, and so that can throw things off significantly. Now, once we've done this, it's pretty straightforward. You can take any map. In this example, we have a map of Australia, and if you identify enough locations on the map and then identify those on a referenced map or data set layer, you can then combine the two using the spatial information from one and the shared locations, the control points, if you will, and you can take the scanned paper map or whatever other thing you're working with and correctly position it relative to the globe. And this is kind of represented here with this classic map draped over an image of the Earth. Now, this whole process is called georeferencing, and basically it's the identification of known locations on data with an unknown spatial reference and corresponding same location on data with a known spatial reference. So imagine two data sets, or two maps, if you will. One, you have a known spatial reference, WGS 84, blah, blah, blah. The other, you don't know what it is, you just have the image. But in the image you can find, oh look, here's that intersection, here's that peninsula, here's that island, here's that whatever. And if you can find pairs of these things between the two data sets, it's basically the same thing as if you think of aligning the unreferenced data or map to the reference data or map. So here's what we're talking about. We've got two photos. One has been georeferenced already, the other one has not. And so to georeference it, how do we do it? We find locations that we can find in common. In this example here, we have these control points. And so if you look at the bottom right, you see a control point that's at the end of that parking lot. And on the image on the left, you highlight the exact same point. And then the top right, you see that we're at the sort of the end of that building, and we find that same location on the other one. And basically you do this repeatedly, and after you acquire enough control points where you can clearly identify one to the other, the math can code work. And so basically it would look something like this. Here is an example where we have 1, 2, 3, 4, 5, 6, 7, 8 different control points that we identified on the map and on the image. And all we have to do is twist things around to line those points up, and we do it by rotating, skewed, scaled, translated types of process. And so here's what those look like. Rotational means you literally just imagine taking the darker color is where it starts. No, I got that wrong. The lighter color is the initial starting spot, and the darker color is where it goes after you make that adjustment. So with rotation, it's literally just like you turn it. And so if you imagine that light green polygon there in the top left, and you just sort of grab it and twist it to the left, rotating around that center axis, then that's rotational adjustment. Skew basically means that you leave the top and bottom fixed on the same plane that they're in, and you just shift them left to right, and so it makes things kind of diagonally, and it stretches and distorts a bit. Translation is another common thing that happens, and that's literally when something is the right shape, it's in the right configuration, it just needs to be shifted in some direction, maintaining its current position and configuration. And then scaling is where something just isn't the right size. It needs to be made larger or smaller. And so here is another example. We've got this map of Europe versus this other map of Europe, and they've added control points to things in both, and then basically once they've done that, you can see how this has sort of twisted and bent the older map image on top, and how it will then align with the data on the map behind. So what do we do after that? Well, we have to either update the georeferencing or rectify the image. If we update the georeferencing, it literally just keeps all the information on those control points so that the software can read that and understand how to maneuver that image around to make it fit. Now, I failed to mention on the previous slide, I had at the bottom it said root mean square error, RMSE or something like that. That is how we gauge how well our georeferencing fits. And it looks at this process of where a coordinate is on the known map and where it is on the georeference map after we apply the mathematical fit. So you create all these control point pairs. Basically, you just do regression. And as you know with regression, that linear function doesn't always mean that every point lines up perfectly on that line. Some are a little high, some are a little low. So if we were to look at, for example, the root mean square errors, what we're looking at is how far above or below the line those data points are on average. And the smaller the number, that means that closer they are to the regression line, meaning the less amount of error that we have, and the better the fit. Now, and the way we measure that is we apply all the math from the regression between the two images, and then once we do that, we say, okay, what is the value of the location on the new map versus the old map. And if it's perfectly aligned, then it'll be the same, and if it's not perfectly aligned, there'll be a little difference. That little difference, that residual, that error, that's how we score these things. Alright, so back to what I was saying here. If we don't update the georeferencing, we have to go through this process of rectifying it. And rectifying it basically creates a brand new image, and it resamples it from the old one. It does increase the amount of distortion. It can cause some blurring and smoothing of your data. Here's another good example of a really old map of London, of Exeter College. I think it's in London, I can't remember. And of course a current aerial photo of the countryside. And by identifying common things like specific bends in the river, specific intersections on roads that still exist, and that sort of stuff, we can make this very old map fit right on top of the data of the current information.